Goody! A challenge! This is going to be fun.
We've already looked at two kinds of proofs. A two-column format, which gives you a sequence of statements with their corresponding reason, and a paragraph-style proof, which is basically a narrative form of that two-column format. What we're going to look at now is what's called a coordinate geometry proof, which kind of uses the three fundamental formulas that we studied with coordinate geometry to prove arguments much like those other two forms do. So let's start with a basic example to see how these coordinate geometry proofs actually work. So say I want to prove the theorem that the diagonals of a square are perpendicular. I'm first going to need to create a square in the coordinate geometry plane. I'm going to do that by letting OQRS be a square that has a vertex at the origin and a side of length A, and I'm going to construct that square in the coordinate plane. Notice that as I graph it, OQRS has one point that's on the origin. I go up A units to get my next point, so that'd be at the coordinate 0A. I go over A units horizontally to get my next coordinate, AA. I go down A units vertically to get my coordinate A0, and that also gives me a side of length A. So I have four congruent sides, and they are perpendicular to each other because they are composed of horizontal and vertical lines. Once I have that, I'm going to use this diagram and my coordinate geometry formulas to prove that the diagonals of a square need to be perpendicular. So I'm going to go to my diagram and create diagonal QS and diagonal RO, and my goal is to show that these two diagonals are perpendicular. Well, recall that in order for lines to be perpendicular, their slopes are negative reciprocals, so that the product of those slopes is -1. So my goal is then to show that the slope of diagonal QS times the slope of diagonal OR is equal to -1. So in order to do that, I'm going to calculate those slopes. The slope of QS is equal to change in y from Q to S is down A units, that'd be -A, and over from Q to S A units, so that would be -1. The slope of RO, from O to R, I've gone up A units in the y direction and over A units in the x direction. That gives me 1, so that the slopes, or the product of those slopes, is just -1 times 1, which is in fact -1. Therefore, QS must be perpendicular to RO. And those are the diagonals. So the diagonals of a square are perpendicular, which is exactly what I was trying to show. Now this was a very basic example just so that you could see how to set it up. Now this is a theorem that we've actually proven using two-column format before. So why might a coordinate geometry proof be better, or when might you want to use a coordinate geometry proof versus a two-column format proof? Well, for situations that it would be very hard to prove it in two-column, or a lengthy proof, like 15 plus statements, can sometimes be done rather quickly using coordinate geometry formulas, such as this example. Say I want to prove that the medians to the legs of an isosceles triangle are congruent. Well, first I'm going to create an isosceles triangle in the coordinate plane. I'm going to let OPQ be an isosceles triangle that has a vertex at the origin, a base of length 2A, and a height of B. And I'm going to construct this in my coordinate plane. So I'm going to place one of those vertices at the origin. I'm going to place its base along the x-axis so that I move over 2A units. And the height of this triangle would be B. Now, I strategically made its base length 2A because I know that the vertex occurs in the middle of the base for an isosceles triangle, so that it easily gives me the coordinate the x-coordinate of the vertex point, which is A, and since its height is B, that y-coordinate of that vertex would be B. Once I've done that, I'm going to draw in those diagonals, OR and QS, which are the medians that go to the legs of the isosceles triangle. And my goal, or what I'm trying to prove in this case, is I'm trying to show that SQ is equal to RO. So that's what I'm trying to show. So I'm going to calculate the lengths of those. But before I can figure out what the length of SQ is, I need to know what the coordinates of S is. Well, since it's a median, it occurs at the midpoint, which means that these two segments are congruent, and I can use the midpoint formula to get the coordinates for S. Now recall that the coordinates of the origin are 0, 0. So if I'm getting the midpoint, midway between 0 and A would be A over 2. So that'd be the x-coordinate, and midway between B and 0 would be B over 2. So that's my coordinates for S, and while I'm doing that, I'm going to do the same thing for R. It's a midpoint, so I can use midpoint formula to get those coordinates. Midway between A and 2A would be 3A over 2, or 3 halves of A. And midway between B and 0 would be B over 2. Now that I have the coordinates of both of those midpoints, I'm able to calculate those two distances. So I'm going to calculate the length of SQ using my distance formula. So it's going to be the square root of the difference in the x-coordinates from S to Q. So I'll start with S, I'll have 2A. So I'll start with S, I'll have A over 2 minus 2A squared. That's the x-coordinate of S minus the x-coordinate of Q, plus the y-coordinate of S, which is B over 2, minus the y-coordinate of Q, which is 0, squared. Okay. Now, in order to combine these two values, I'd need a common denominator, so I'm going to do some scrap work underneath. I have A over 2 minus 4A over 2, which would give me negative 3A over 2. And that whole value, is in these parentheses, is squared. And when I square negative 3A over 2, I get 9A squared over 4, plus, well, B over 2 minus 0, which is B over 2. And when I square that, I get B squared over 4. So that this entire value is just the square root of 9A squared plus B squared all over 4. But the square root of 4 is just 2, so I'll extract that from my root, and I get this. So that's the length of SQ. And now I just need to also do the distance formula on RO to find its length. I'll start with R, and I'll have 3A over 2 minus the x-coordinate of O, which is 0, squared, plus the y-coordinate of R, which is B over 2, minus the y-coordinate of 0, squared, which again gives me the square root of 9A squared over 4, plus B squared over 4, which we also know reduces to the square root of 9A squared plus B squared all over 2. Well, since SQ and RO have the same length, by definition, they are congruent, so that the medians of the legs of an isosceles triangle are congruent. To the legs of an isosceles triangle are congruent. So how this differs from a paragraph style or a two-column format proof is we don't have to write out the theorem that we're using to justify each of the arguments we're making. We're actually doing algebraic verifications of the ideas that we're using. The main aspect of this coordinate geometry proofs that's essential is being able to set up a generalized diagram that represents the given situation and then applying our coordinate geometry formulas in an appropriate manner to verify the information that we're trying to prove. We'll go over several more of these examples in class tomorrow. Please prepare any questions you have from this video and we will address them at the beginning of class.